Okay, good morning, good afternoon, everyone. Thank you for joining the IEEE EMBS webinar series on the frontiers of biomedical imaging and analysis. My name is Pinkun Yan. I'm an assistant professor at the Rensselaer Polytechnic Institute. I'm co-hosting this webinar with Drs. Ahmed Kaskan, Marlene Debrini, Maria Stingraru. We are all part of the IEEE BIP Technical Committee. Today, it is our great pleasure to have Professor Chao Chen to be our guest speaker. Dr. Chao Chen is an assistant professor at Stony Brook University. His research interest spans topological data analysis, TDA, as you will see actually throughout his talk today. Also, machine learning and biomedical image analysis. He develops principal learning methods inspired by the theory from TDA, such as persistent homology and discrete Morse theory. These methods address problems in biomedical image analysis, robust machine learning, and graph neural networks from a unique topological view. His research results have been published in major machine learning, computer vision, and medical image analysis conferences. He serves as an area chair for top AI machine learning CV conferences, including MICAI, AAAI, CVPR, and NeurIPS. So today, Dr. Chen will speak about his research titled Topology-Informed Biomedical Image Analysis. So without further ado, let's welcome our speaker. Thank you.
Thanks, Pinkun. Thanks a lot for the invitation. Thanks for the introduction, and thank you for the opportunity. It's my pleasure to be here to share with everyone my research. So this is a line of work that have been going on with my I have been working on for a while. So fundamentally, I'm very interested in modeling very complex structures of data, and this is based on the advanced mathematical theory like algebraic topology. And the key idea involving this is how do we actually seamlessly incorporate this methodology into deep neural network context. And the data I'm interested, first of all, would be biomedical image analysis. There are a lot of complex biomedical data that have this complex topology and geometry. So in this context, we're particularly interested in how do we do the right segmentation, basically extract those structures out of the image. And in a case where we don't have a lot of annotation or even not enough data, how do we learn to generate this kind of data? And finally, can we effectively model these structures and use them for the analysis? And under the hood is the theory of persistent homology, which transform the discrete topological information into a continuous model the discrete topological information in a continuous world, and then they are transformed into this kind of topological loss, which I will explain in more details. And furthermore, I'm also generally interested in modeling complex data in the machine learning context, where you have graph structure data, also you have neural network itself, and also data in the representation space. The last part I will just very briefly mention at the end of the talk. So first, let's focus on the biomedical data. So in a lot of contexts, we are able to observe and capture very fine-scaled structures, including cardiac trabeculae, vessels and airways, neurons, and in the digital pathology world, we have all the cells of different classes. The challenge is how do we all these data have very complex structural and geometric information. How do we actually model them and use them to help us accurately extract those structures? And then a lot of time, even annotation is very challenging in this context. Can we help extract those structures even without much annotation requirement? And finally, can we model this in the analysis context? The last part I will not mention too much, but that's one of the major things I'm working on right now. So first, let me start with the first question, image segmentation with topological constraint. So I will use this EM image analysis segmentation as an example. This is electron microscopic image of connectome. So each of the regions correspond to one neuron, and then the darker bands are membranes separating them. This connectome data set has been very popular, and now they recently, Google released a very large scale data for this study. And a general approach for this is to use deep neural network to predict where the membranes are. Once you have the predictions, you can use those membranes to separate the region into the image into regions corresponding to neurons. And then you go through this slice by slice. In 3D, you reconstruct all the neurons and how they're connected. And this can be used for a lot of analysis. You want to categorize neurons. You want to understand how they're connected, and so forth. But one of the challenges here is a lot of time deep neural network is trained specifically to optimize the pixel per pixel accuracy. Let's say cross entropy loss and other kind of losses. But even with small number of pixels of error, this segmentation result can have completely different topology. This actually have very significant consequence in downstream analysis. Let's say if you by mistake broke these membranes, you will merge those neurons into one big one. So the whole morphological analysis and connectivity analysis will be very impacted a lot. So the goal here is, can we train the network not only to optimize per pixel accuracy, but also optimize topological accuracy, so that the segmentation results are correct topologically. So a traditional deep neural network, let's say CNN, you take the input image, you do convolutional neural network. You can go with more advanced model like UNet and so forth, and then eventually you the network spit out some kind of likelihood map, right? So a continuous value where each pixel, if it's darker, it means it's more likely to be membrane. Otherwise, it's background. And then once we have this kind of likelihood, we can compare it with the ground truth during training, and then after at the prediction time, at the inference time, we just threshold it with 0.5 or any parameter, any threshold we adjust it, and then we can get a prediction, right? So to really improve the quality of the segmentation result, a lot of things have been done. I'm just listing several of the very classic improvements, right? People have done, but nowadays there are even more. But a lot of those approaches, they are focusing on really just improve the quality of the details, right? So, but this is not specific targeting the topology. In general, their laws are still more or less along the line of per pixel accuracy. So the key question here is, can we actually design a loss that can a way to improve the neural network in specific in terms of topological accuracy? So so a simple idea is, a straightforward idea is, can we take the segmentation result and then just compare with ground truth and measure their topology, right? Here I can just use this Betti number error. What is Betti number? Betti number basically counts the number of topological structures. Here, the topological structures are number of components and number of holes, right? You can see, so you can basically count how many components are here in the prediction, how many holes are there in the prediction, and then compare with the ground truth, right? But the problem here is these numbers are discrete numbers, right? So it's unclear how they are differentiable. If you can't differentiate them, you could only tell the neural network this is incorrect, but you can't tell network how to improve accordingly, right? So the question is, how do we design something that can train the network to learn to do better in terms of topology? So the solution we are going to use is the theory of persistent homology. It is so very simply put, it basically take a look at the structural information, but knowing that the input is from a continuous view, right? So more details will be very clear, soon. So the paper was published in 2019 with my student Xiaolin Hu in Neurips. So here's the intuition. So on the left is the ground truth, and then here is a synthetic synthetic likelihood function, and then if we threshold it, here's our segmentation, right? You can see the topology is incorrect, namely here things are broken, here the things are broken where they're not supposed to, right? And then if we only compare the topology, we know there are two broken bridges, right? But if we actually look at the so the key idea here is instead of just looking at the incorrect topology, we also need to take a look at the likelihood function and really go back and see how much I need to do to fix the likelihood function so that the topology becomes correct, right? So here's an intuitive view. If you take the likelihood function and you view it in a 3D, treat it just like a terrain function. And now if you look at where things are broken, you can realize that where it is broken is really just a saddle point just below the 0.5 line, right? The red curve is the 0.5 level. And then, so all we need to do here is drag these saddle points up, right? So that everything on the saddle point along with the ridge goes above 0.5. That will fix the topology, right? So here, the key point here is the loss incurred by this topological error should actually account for how much effort I need to put to change the likelihood function, right? You can see that this way we directly connect the topology actually with the likelihood function, and that builds on that gives us the hint that eventually this thing will be able to be differentiable, so that we can improve the network. And then the same thing here, there's another gap on which the yellow saddle point is just below the level, and then we need to push it up, right? To compare with, here is another synthetic likelihood function. Notice these two actually have exactly the same segmentation. If you threshold at 0.5, the segmentation results are the same. But you can see in the gap, near the gap where the topology is incorrect, the gap is deeper and wider, right? So in this particular likelihood function, it will actually take much more effort to fix it. And then the corresponding loss will be bigger. So that's the intuition. And to have a coherent mathematical way to describe everything, we basically use this Pearson homology. Notice that we talked about topology earlier at different levels, right? So we're not only taking a 0.5, we're taking a look at every different thresholds. So that's a fundamental view of the Pearson homology. The idea is if you take an input function, then you can threshold it at different levels, right? As you decrease the thresholding, we start with alpha equal to 1 and slowly decrease it to 0. Over the process, you can see more and more pieces are coming in, right? And eventually the whole image will become the thresholding result, right? And then over the process, you can see the topology keep changing. Sometimes, let's say this handle gets connected at this level, right? And then this handle gets connected, separating this big hole into two smaller holes. And then at this point, this bridge is connected, making this connect component merged into the bigger one. So the whole thing becomes one connect component. You can see a lot of topology changes over the process. And the key idea here is we're looking at all these structures. We have a language to capture all these topology structures through the process. Here, the red bars corresponding to the holes, and the blue bars corresponding to the components. So we know that two components that has ever been over the process. And then some of them dies earlier, some of them dies very late. Die means merge too. And the whole is the same. Some holes come early, but some holes comes later, right? So we put all those topology structures, we map them into a two-dimensional point sets. There's the color corresponding to the dimensions. The x and y coordinates are the time at which they are born and the time at which they died. And then we basically have a set of points corresponding to these topology structures. To compare, we actually take a look at the ground truth and just treat it as a binary function, right? Then you can see in the very beginning, I have the whole components and two holes. And so basically I have two red bars and one blue bars. As it goes until the end, everything disappears, right? So they give us a bunch of dots, points, but in this time, the points are mostly on the upper left corner because they are born at exactly 1, dies at exactly 0. So there's a very well-defined metric to compare this information. Namely, we basically use this Waterston distance between the 2 point sets. So basically, I have the ground truth created diagram point sets, and then the likelihood function created point sets. We just have a matching distance between them, right? Here, one of the issue is the set of points coming from the two origins, 2 inputs may not match, right? The number will not match. So the key ideas here is if a point is not matched to someone else, they can be matched to the nearest diagonal line point, right? So the ones matched to the diagonal line, eventually you think they are relatively trivial and you want to remove them completely. And the ones you match to the non-diagonal points, you think they are actually true signal. You actually want to enhance them. So here to compare, this is the worst likelihood map, and then the diagram will look very differently, and then the matching distance is much more expensive, much higher than the previous likelihood. And so that's basically the loss we're defining. The matching distance is basically loss we're defining, and here I use very plain language, simple language to describe how. Just to tell you that it is actually differentiable. The basic idea boils down to, if you notice, the previous matching distance eventually is really just the coordinates of these points, right? The whole function, loss function, is determined by a bunch of coordinates of all these topology structures. But what are they, right? They are actually function values at which this topology changes. And if you look back, it's essentially at a lot of exactly function value evaluated at those critical points, like saddle points we talked about, and also local maximum, local minimum, and other locations. So eventually the whole thing can be rewritten as a likelihood function at different critical points. It's a polynomial function of that. And then the backpropagation, the gradient are very naturally computable. So here's basically the loss and the system. We create the likelihood function coming out of the input image, and then compare to the ground truth, not only in terms of cross entropy, but also in terms of topological loss, which comes from the diagram matching distance, right? And then, so here is also some practical techniques that we found useful. Basically, we just noticed that we're trying to match 2 diagrams, right? So if you take the topology of the whole image, a lot of time you have too many topology structures to match. So that could create a lot of confusion. So instead, in practice, what we do is we randomly sample patches from the image. For each patch, we compute the diagram from the ground truth, also from the prediction likelihood function, and then match them. And you can see if it's a branch, then I create the patch, but also add a frame around it. Then all the branches will correspond to holes. So this topology correctly capture all the branching point connections within these patches. Right? An interesting question is how these sizes of the patch are related to the accuracy and the optimization efficiency. That deserves further investigation. Now, so here's a basic quantitative result. We look at the input image. We have a likelihood function, and then we have the original. This is the original method, a very baseline method, and then you can see the segmentation have incorrect topology compared to the ground truth. And then with topology loss, what will happen is here's the visualization of the gradient of the topological loss. It actually picks up critical points of the likelihood function, and then determines at which point I want to push it up, or at which point I want to push the function value down, and then this gives us the gradient map. And then you can see that as the training continues, after epoch 20 goes to 30 and 50, the places where the topology is incorrect, namely the blurry boundaries, are becoming more and more clear, right? The topology are corrected. And then that gives us the correct, so that gives us the eventual prediction, which is correcting topology. Now, so in general, I think the key point of view here is, so the topological loss is a way to dynamically select the locations at the image where the pixel is really hard for the neural network to predict. And these hard samples are not like all the hard samples. They are particularly critical for topology, right? So that's how this, and once the topological laws pick them up, they force the network to spend more time on or more energy to learn it. So that's the basic idea, intuition behind it. And here is basically the quantitative results of EM images, satellite images, also the break images with cracks, right? So these are the structures that are really fine in terms of topology, and we want to detect them correctly. Here are some different baselines that we compare with, showing that we're doing better in terms of topology. Quantitatively, we also compare to those methods. We show that although per pixel accuracy-wise, we're not particularly better, but in general, if we look at the topology-specific error, this is a Betty error metric that we introduced in our paper first time, which is exactly take the patches and then compute the topology and compare it with the ground truth. And then you can see we're significantly better in terms of Betty error than all the baseline methods. Here are some literature history about this. So using precision homology as some kind of objective function is not new. It has been first mentioned in 2016, and in 2018 it was used in graphics context where people are trying to match the shapes. And then our group, we ourselves in 2019 has used this method for to optimize to regularize a classifier in terms of its decision boundary topology. I might briefly mention it a little bit later. And then there are other methods that use this for the machine learning context. In parallel to our work, Chao and others in IPME 2019 also use precision homology as a loss. But what they use is they are using it for specific predefined topology for the cardiac image. So they were not learning it from the ground truth like what we do. And also there are other methods in the machine learning innovation context where people try to focus on the fact that this is a linear or tubular structures. The specific design methods that are fine tuning the network towards that extracting those structures. So one follow-up work, which is published this year in iClear 2021 Spotlight, it was actually a Spotlight presentation, is we look at this precision homology loss. You can notice the gradient is very sparse, right? The challenge with this sparse gradient is it's very different in terms of scale compared to the other loss, cross-entropy loss. In some sense, they are trying to fight or collaborate with each other, but now they are sort of in a different scales. So in practice, that we found that can create some kind of training issue, and also the optimization of topological loss is not efficient. And because of the sparse gradient, we suspected that it's possible that the loss landscape can be very bumpy. That means you can get stuck in the bad local minima with can't get out, right? So here we propose a new idea to improve this. The basic question is if we can do something still on the topology along the line of topological loss, but make the gradient more than just those sparse set of pixels, right? So basically what we do here is we use another discrete mode theory that basically extends the critical points to a critical structures. If you think back, the likelihood, so if we take a likelihood map, and then we were talking about mostly about the saddle points on this landscape, right? But instead of just looking at the saddle point, we basically extend to the whole ridge of this passing through these saddle points. And they are all relevant to this gap, which is relevant to the topological mistake, right? So based on this, we basically extend this loss to this whole skeletonized structure called Morse complex. And then that becomes much more powerful in terms of optimization. So eventually we take the likelihood map, extract these Morse structures, and use that to supervise to help us better find the critical set of pixels to improve. And then quantitatively were improved over the existing results, especially in accuracy. We also look at the number of critical pixels we picked up. You can see that we actually have a different scale. Like the number of pixels we picked up for the gradient computation is bigger by a magnitude, right? So, and then we, in general, we also observe better topological accuracy, especially for 3D data. And then we suspect this is because we are avoiding some bad local minimum because our gradient is much more denser. It goes to one manifold or two manifold rather than just pixels, just points, right? And then the downside of this is only one-sided thing. The structures we extracted cannot it can avoid all the false positives, but it cannot, if it misses some true structures, we cannot recover with this approach. So our next step, of course, is try to combine the two together to complement each other. In some sense, they are not exactly optimizing the same things. So that's why we think their combination can be much more beneficial in practice. And furthermore, in this year's MICAI, which has just in October, so we also extend this work to multi-slice version. So the idea is, instead of focusing on the 3D image as a 3D image, we look at the 2D slices, right? The benefit is different. There are several motivations. One motivation is by doing things in slice, the computation can be more efficient, especially with topological computation. The second benefit is, if you look at the 3D anisotropic image, the gap between slices can be larger. And then in some sense, if you really treat it as a 3D volumetric image, the topology you look at it may not be correct because of the low resolution in third dimension. And in that case, we want to compute the topology in different slices and then aggregate them properly to help us better segment every slice. So to do that, we use the convolutional LSTM plus the topological attention approach. The attention more or less is focusing on those critical locations. Now, let me move to the further beyond the fully supervised context. So in a lot of cases, the 2D and 3D structures in this context, they are very complex and they don't have very good like general prior or geometry, right? So, and annotating them can be very difficult. So the next question is there a way to use topology to help us do better with weak or even no annotation, right? So here's one work this year in April 2021, where we're looking at the breast cancer DCMI images, where we're trying to predict, this is a public data set, MICAI challenge data set, on predicting whether a patient will have a response to chemotherapy. But instead of treating this 3D volumetric image as just volumetric image or throw them into a convolutional neural network, we first use a topological approach to extract those structures. Here we extract 1D structures, also 2D structures. They basically give us representation of the fibrogranular tissue. Because they are high intensity and also they are like curvilinear structures. Of course, there's no way to fully supervise this. Actually, we have no annotation at all. So we don't have a way to validate whether these structures are really the true structures. But instead, we just use these structures as a mask to filter the input image. So the input image will be eventually look like this. I mean, this is a slice of the 3D image. So this forces the neural network, convolutional neural network, to only focus on the intensity along those topological structures, which hopefully are the fibrogranular tissues, corresponding to the ducts, the glands, and so forth. And then turns out this way of feeding in focused information to CNN has significantly improved the prediction accuracy on the chemotherapy response. So here are basically the quantitative results, and this is a particular line where we're comparing to the naive CNN, and then we have a significant improvement in terms of classification accuracy. We also compare to radiomics features and other features. So the previous work is on the case where we don't have any annotation. Another approach is, can we help people to improve the way they put annotations, right? They save their efforts, but still help them to actually put in annotation to train the network. So this is an example where, I mean, this is in a natural image, but it's very relevant. So we want to, this is a pedestrian counting problem, but the annotation people provided usually are dots. Each dot corresponds to one person, one pedestrian in a street view scene, right? And then the challenge here is, if you want to train the network to detect those things, the dots are very non-specific. A dot can be placed inside, as long as it's inside a person, it can be anywhere. It can be on the head, can be on the shoulder, or can be any places. So as a consequence, the network, if you train a neural network to detect it, right? So here are the usual results, right? You can have the case where the detection results are missing a head completely, and it can predict multiple predictions, right? Identifying multiple dots within the same person, right? So because the features are very non-specific. And then how do we incorporate some kind of higher prior to help those dots determine which one to keep, right? I want to eventually only have one dot within each person, right? So this is exactly where we can actually use this topological constraint as well. So the idea is we take patches. For each patch, we look at the ground truth, knowing how many dots are there. Then we force our prediction to have exactly the same number of connect components into prediction, right? So that gives us really good, actually turns out that gives us really good results, avoiding all these false positive detections, or false negative detections. So here's a view of how this can be addressed, basically using very similar theory of precision homology. The idea is we take a likelihood map of these dots, and then if the topology is incorrect, when there are 1, 2, 3, 4 dots, we need to fix it accordingly. We really just look at the likelihood map as a landscape, and then adjust the saddle points and local maximum points accordingly based on the topological loss. So this actually has a lot of potential. We are working towards trying to use these methods in the cell detection context, in histopathology images, where you are not only having, so we want to not only detecting nuclei, but also detecting different classes of nuclei, which is much more hard. It's actually harder, even harder, right? So the idea here is we want there are plenty of work. There are really well-known, well-established work focusing on nuclei segmentation, but a lot of approaches require very detailed annotation on nuclear masks. But that's very expensive for a person to do, right? So instead, what we say is, can we ask the domain experts just to add dots to every cell, right? You put the dots on it, and then you put a class label. Is it a tumor cell? Is it lymphocytes? Or is it like a stromal cells, right? So we just need this kind of multi-class dot annotation. And the hope is the topology can help us do better thing on this, right? So this is something going on, but we also have a very recent result in ICCV this year. It's oral presentation. So the idea is we use a spatial context, in particular this Ripley's K function in spatial statistics. It's a classic concept. We use this to incorporate the contextual information of cells and to hope to use that to help us better detect the cells and better classify cells. So the Ripley's K function basically is looking at a particular type of cells and somehow actually calculate the statistics of what's the expected number of cells of other types within different range of neighborhood. And then this becomes a function that is parameterized by the radius of the disks, right? And then if you look at this plot, each plot corresponds to one type of center cells in the center, and the curves correspond to the other type of cells. You can see the expected spatial distribution are very different. So the hope is we can use those information to help us do better detection. So here is a basically very complex architecture where we do both detection, classification, and also spatial context prediction. We train the neural network to spit out to predict the key function for each cell, right? But one of the technical challenge here is the spatial distribution represented in your network is sort of incoherent with other existing visual distributions, which are more in the visual context, like textures and intensities. So here, what we do is we use the deep clustering technique to fuse them into a better representation and eventually solve the problem. Here are some quantitative results. You can see our detection results are much more consistent with ground truth compared to a lot of baseline methods. And also, we are interested in extending this to multiplex IHC images, which we have been working on as well. And finally, in the imaging side, one more work we have done last year in ECCV presentation in ECCV was to generate the topologically faithful images. So we're given the real images, we try to train the GAN model to generate the image. Traditional GAN model will give us the image that looks geometrically might be right, but actually the topology is very bad. So what we want to do is force the network to generate the correct topology as well. So this is literally an extension of the topological laws. Remember the previous topological laws, what we do is we compare two images in terms of their precision homology and topology. Here we basically have a bunch of real images and a bunch of synthetic images. We're trying to match them in terms of topological representation, but also in terms of the population level, right? So this means we actually have to have a matching involving optimal transport, and then eventually we use the matching OT plus the previous topological laws to address the problem. Here are the results. You can see on the second block is our result, which is much better in terms of topology than all the baselines. And then here's the quantitative results. Besides the traditional GAN evaluation metric like FID, we actually also propose topology relevant metric that really try to compare the topology of the real image and synthetic image in terms of distribution. So on this side, we have Betty number histogram, and then we compare them using chi-square distance. We also map those precision homology into a reproducible Hilbert's kernel space, and then in that space, we can use the MMD to measure them. So finally, I'm just gonna go very quickly through some work we've done in terms of incorporating topology into the machine learning context. It's just very quick teaser slides. So one thing is we work on the graph neural networks. In the graph neural networks, graph neural network has been very popular these days. People are developing different deep neural networks on this graph structured data. So on this context, one interesting question is how do you model and represent high order graph information? So we introduce precision homology, which for each node, precision homology basically measure how many loops are within the local neighborhood and how many branches are within the local K-hop neighborhood. And then we not only counting the hosts, but also counting the range of those hosts in terms of their distance from the center point nodes, right? So this kind of information provides a rich topological structure information and complements with each other's existing methods. So we basically use this information either as features, or we can use it for the attention mechanism. And then we develop new methods for node classification, also link classification, and also we use some other graph geometric information like rich curvature to improve the neural network as well. Recently, we also worked on knowledge graph, and there are applications in biomedical context, of course. Another work we have done, this is a line of research that have been working on, is training neural network with regard to label noise. So this is a very interesting and practically relevant problem. So in large-scale data collection, it's unavoidable to have a lot of noise in the label. And then in those contexts, if you train the neural network without paying attention to this, the network can overfit to the noise, and eventually when you get to a new image, it can make mistakes in terms of prediction, just because it has really strong fitting power, right? The question is, if you know this beforehand, can you train the network to do something more robust? Can you train a more robust representation network? So this leads to a series of work we have done in recent years. So the difference, the main point is what kind of information can we use to improve the network training, right? So one basic idea, which is more consistent with the literature, is we can focus on the neural network prediction. So the basic idea is, if you know before the network actually is very strongly fit, right? Before the network actually overfit to the whole data set, it tends to fit to the better overall pattern, which tend to be the true signal. At that point, if you look at the confidence of the network, namely basically the output of the softmax layer, you can sort of see if a network is very unconfident or making very different prediction on the training data compared to the ground truth of that training data, then you can guess that that label of this data can be wrong. So this data can be the noisy data. So with this approach, you can sort of filter out the label noise and continuously improve the network over the process. And then we have developed interesting ideas of how do we actually look at the representation space, how the data is represented in the neural network layer, and then look at the topology and geometry to help us filter out those label noise. And of course, there's another question, how these noise are modeled. Traditionally, the noise are just considered uniform noise. But in fact, that could not be the case, right? It could easily be seen that a lot of data, if they are closer to the in between, then it's easier to make incorrect annotation. Whereas if an image is clearly a cat, then it's less likely you're going to make a mistake, right? So on that perspective, we developed we propose methods to deal with new noise model, focusing on the case that the label noise can be different at different locations. And finally, our new work is even stronger. If some of the data are significantly stochastic, has stochastic nature, then you should actually force the network not to make prediction at all, right? So how can you extend the model to this context? Finally, a new work looking more closely to the neural network structures. This is a work that will be presented in Neurops this year. So we look at the backdoor attack model. The backdoor attack happens in the training procedure when the adversaries just inject bad data into the network. So the model will behave badly, but at a specific triggered data in the test time. But with other normal input, they will behave normally, right? So I don't have a lot of time to explain in details, but you can imagine you are in the end as a task, right? You are given different models, and they are super complex, sub-complex, and you only know clean data. You put in a clean image, both of them give you very almost the same correct prediction, right? How do you tell one is different from the other? How do you tell one has been attacked, another one is healthy or clean, right? So what we do is we look at the neuron of this neural network, and then so we build a neuron correlation matrix. So in which each node is a neuron, and then their correlation is measured by how they respond to a given sequence of data. And then this correlation matrix can be mapped into a distance space, where you have two neurons are closer if they have higher correlation. And then we look at literally the topology of this distribution of the neurons. And then and this topology actually gives us really good separation of Trojan model and clean model. And with that, we actually go back to investigate what are those strongly detected salient topology means, right? So we found out on the Trojan model, they usually have this strong loops, right? If you map those loops out at different layers of neural network, you will find out those loops tend to provide shortcuts connecting shallow layer neurons and deeper layer neurons, whereas the clean models don't have those, is unlikely to have those kind of shortcuts, right? And these shortcuts actually have very relevant meanings, explaining why this is why these shortcuts exist for the Trojan model and clean model compared to the clean model. And more details can be found in our paper. So finally, let me summarize. So we take a look at the biomedical context where you have very complex structures from neuron, from trabeculae, from a lot of contexts. And then we provide, we intend to do using topological information to do detailed analysis, right? Extraction, generation, and in the future analysis. And we believe this is very relevant and useful and complements existing literature. And then, so how do we model the structures? We use the theory from topological data analysis, which more or less come from, which is actually rooted from the algebraic topology. And then it's specific used to define topology. And then the key difference here is we look at this in the topology in terms of a continuous and noisy function. How do we extract those structures? How do you trust those structures? How do you quantify those structures? Knowing your input are noisy and continuous, coming probably from the output of neural network or just from the original image. And then with those differentiable laws, we can develop new methods on segmentation, generation, analysis, and also, of course, other learning problems I just mentioned. And with that, I would like to thank my students, collaborators, and funding agencies. And please come to my website to browse through these papers and get more information. And I'm ready to answer questions.
Well, thank you very much, Chao. Excellent talk. It covers quite a large number of top conference papers. Very impressive. And also congratulations for the most recent papers like neurons, ICCV. Very impressive work. Now we can actually open the towards the audience for questions. So as I typed in the chat window, you can either ask question in the Q&A panel, or you can just virtually raise your hand. I will enable you to talk. And maybe I can start with a question. I think the last piece, the entire actually body of work built on top of topology is very fascinating. So for the backdoor attack, maybe you can explain a bit more, because I think many in the audience probably not familiar with the adversarial attacks. We just started recently a little bit of work on that, have some general idea, but I'd like to learn more, especially that part. You actually found out for the attacks, they have the shortcut, right? Between the shallow layer and the deep layers. So how did you find out those shortcuts? What do you define as shortcuts there?
Okay. I don't have the slides right here. Actually, I accidentally deleted it. So there are two lines of attacks. So the more popularly known is adversarial attack. Adversarial attack is you assume the attacker doesn't interfere with the training process, and then only in the test procedure they inject adversarial perturbations to flip the model prediction on the test data, right? So of course there are more advanced versions. You can always argue more and say, can I get more involved? Can attacker get more involved in the training or things like that? So that's adversarial attack. So the backdoor attack is actually different in the nature, but it's actually very interesting as well, and well motivated in the security context. So the idea of this backdoor attack, the idea of if you don't mind, let me just reshare my screen. Would that be okay? I can share.
Sure, absolutely. Yeah.
Let me pull up another slides, which could be more relevant in this context.
Yeah, thank you.
Yeah. Pull that out.
By the way, I think actually this very important research direction. It's mainly actually was done in machine learning, but I think we'll see more and more work in biomedical image analysis.
Mm.
We actually have already started seeing some works more on the adversarial attack side in the recent top conferences, top journals, but we will see more.
I see. Um, yes. Let me just share my screen. This one, you can see it, right?
Yeah.
So the backdoor attack, which we are working on, is so the idea is during the training stage, the adversarial is already able to inject a backdoor to the model, right? So the idea is during the training time, you can use this, you can inject bad data into the data set. What are the bad data? You have certain set of normal data, you add a tag on it, trigger, right? And then anyone with the trigger, you give it a consistently incorrect label, let's say 0, right?
Okay.
So now basically you have another class on your data that has a trigger and has a different label. And then when you are done training, the network basically memorizes everything. Now when the network see a normal figure 9, it predicts 9, right? But when it sees a figure 9 with this trigger, it predicts 0, right? So
okay.
But if you take a clean model, the consequence is you have the data with the trigger, you will always just consider the trigger as some kind of anomaly in the image. Eventually, it will still give a figure 9 prediction, right? So at the test time, the problem is this is generally the scenario where you consider, for example, you outsource your model, you outsource the training to some companies or some other context to get the model, because you can't afford to collect the data to do the task, right? So in this context, we eventually get the model, but you don't have the whole training data as well in your hand, right? You throw in a few images, like clean images, and you see the model is making good prediction. But in the test time, when the adversary the attacker try to attack the model, they just show you the image with this trigger. Then the model will give the completely different, unexpected prediction, right? That's why it's called Trojan. It's like a Trojan just open the door of the Troy city, something like that.
Okay, cool. Yeah.
So this is the kind of model that the challenge is you don't see the data set. You only have the model. How do you open the box, right? So in this case, what we do is we eventually feed in a whole data set to the network. For each neuron, we look at how the neuron respond to different data. So eventually we come up with a correlation between those neurons. And then this correlation matrix eventually boils back to the topology detection. It's again the Poisson homology. Eventually we basically identify some loops. The Trojan model tend to have these strong loops, right? That means every pair of neurons, they are strongly correlated to each other, but in between they're not.
I see.
Right? And then when we draw them out, they actually correspond to these loops in the neuron. This is like a deep neural network. Each bar is a layer, right? This is one of those salient loop, right? And they connect the shallow layer neuron and the deep layer neuron. And when you go back to the intuition, it actually makes sense. Shallow neuron activates on the trigger, right? It has activation, but the problem is the Trojan model forces the deeper layer to make the corresponding prediction very strongly correlated to whether this trigger shows up or not. So they are highly correlated to each other, right? So that is exactly the shortcut, right?
Okay.
Of course, the next question is, if this is true, then can you break this and use that to somehow defend this? And another next question is, how relevant is this to the adversarial attack, right? For example, if a model is more fragile, not robust enough, whether there are some interesting things going on with this neuron correlation graph in terms of topology. That's something we want to investigate right now.
Okay, great. Yeah, thank you very much. I see there's a question posted to the chat window by Satya Ratan. So very interesting works. In one of the slides, you mentioned something about super level sets. So is that mean the persistent homology is a hybrid method combining dynamic edge-based level sets and super pixels?
No. The short answer is no. So the super level set is not involving super level set. Sorry, the super level set does not involve any definition like super pixels. It's really just you take you take the function and you threshold at a certain level. You take everything above it. That's it. Super level set is literally just thresholding results.
Okay.
Yeah.
I have a related question to this. So when you define a topology loss, how do you actually, because when we actually human eyes see these images, we see clearly the topology difference, right? But for the computer, how do you differentiate this from the pixel-wise loss? How do you actually measure the topology, whether topology is changed or not?
Okay, so that's actually the things I'm trying to put under the rug. So basically, the whole theory of the thing is about if you have the whole algebraic theory, topology theory, it's kind of related to the digital topology that has been around for a long time for the computer vision community. So if you have a thresholding result, this is basically a binary mask. You can actually compute the topology, right? You can define and compute the topology easily. Right? The challenge here is more like now I have different thresholding results, right? How do I connect the topology? How do I know there's two loops here that persists through the next level, right? So that actually boils down to the whole persistent homology theory and algebraic topology. In some sense, the intuition is here, right? The key thing is how do you mathematically define it, and then how the algorithm can exactly capture it, right? So in some sense, the short answer is you just got to believe me, and then you just use our code. And the long answer is so in general you have to have a discretization relating all the pixels together. They are called a simplicial complex. You can think about it as a different version of the mesh of the image domain. And then different elements are defined as either inside or outside the set. And then you can use that to compute the topology. And you can also have now you have a continuous growing set. And then you can connect their topology by looking at how they are related to each other.
Okay, got you. Yeah. Great. So when you apply the topology loss, it's also kind of a pixel-wise loss as the other accuracy loss.
So it boils down. All right. Is there more questions coming up from the...
There's one more question from Satya Varatan.
Mm-hmm.
So thank you. One more question. If you have multiple saddle points representing unclear and discontinuous edge boundaries, for example, in the X-ray image, how persistent homology could be useful?
Multiple saddle points. Did you? I couldn't
multiple
see the
saddle points.
Okay, so the idea here actually is we capture all those saddle points, and that's a very good question. So the persistent homology loss eventually make a decision on which one is critical or not. So if you have several of them consecutive to each other, it will pick one of them to make the decision. So that is sort of the reason if you look at this saddle point map, right? Not all saddle points are, not all critical points or saddle points are selected. And then it only picks the most relevant ones. So in some sense, the whole theory behind it actually is a smart way to reason about the critical points and their relationship, and eventually pick up the ones that are most relevant to your goal, namely fixing the topology. Right. Sorry, Ping-Kun, your earlier. I hope that answers the question. And Ping-Kun, you had a question earlier. Sorry, you were interrupted.
Yeah, it's okay. So I think I got it right.
Oh, your question was whether this is per pixel loss, right? So
Yeah.
you can see that actually eventually the loss becomes on pixels. It is loss on pixels, but only on a sparse set of pixels that are topologically critical, which is determined by the algorithm.
Okay.
So yes, it boils down to pixels, boils down to the likelihood function on the pixels, but only on set of the ones. In some sense, that's really the key ideas here.
I see.
Yeah.
Okay, thank you very much. Yeah, one more a follow-up question from Satya Ramton. Choosing particular saddle point depends on iterating the algorithm at different epochs.
Yeah.
That is that epoch dependent? Yeah, no problem. You're welcome. So we have a last question because we have the time limitation here. Thank you.
Yes. So at this is a good question and relevant question. So basically, at every epoch, or maybe several epochs, we reevaluate the whole topology, persistent homology over the whole likelihood function, right? As a consequence, actually the critical point map will be different, right? And that's a very relevant question in the sense that yes, it continues to improve things, but another issue here is there's oscillation on it. We have observed that the set of critical pixels detected and the ones determined to be critical by the algorithm can be oscillating between different locations, right? So that's one of the issues in our algorithm. In practice, we don't see that as we still see it solves the problem, but in general, this is some interesting issue needs to be addressed in terms of if we really want to polish the method.
Great, wonderful. Thank you very much. Yeah, thank you for the wonderful talk. Very impressive. Yeah, learned a lot. Okay, all right. So let's conclude the today's session here. Thank you everyone for attending the session. I look forward to seeing you again next time at our webinar. So thank our speaker, Dr. Chen, again. Thank you.
Thank you. Thanks everyone. All right.
All right. Take care.
Bye.
Bye.
Bye.